So this is the panel discussion. We have 6 panelists who I will now introduce. So Dr. William Sanders, the director of the Coordinated Science Lab here at the University of Illinois. Dr. Helen Gill, program director for Embedded and Hybrid Systems, the National Science Foundation.
Oops, and CPS.
And CPS. Error in the program.
No error in my bio. It's old.
Okay. All right, Dr. Kabir Barua, Department of Mechanical and Aerospace Engineering, University of Florida, Gainesville. Dr. Joao Espanol. Joao Espanol. Department of Electrical and Computer Engineering, University of California, Santa Barbara. Dr. Kevin Weiss, Boeing, and Dr. Ian Hiskins, Department of Electrical Engineering and Computer Science, University of Michigan, Ann Arbor. So I hope that you have all brought your questions. We have also prepared a couple of topical questions. Our hope is to create a conversation, possibly some debate. So for the panelists, if we ask a question or if you feel that you would like to answer a question, we will try to proceed right to left. So we can use that as kind of an ordering scheme. But if you have something that you really like to say, feel free to jump out in front. So I'll start now with the first question. And at any time, if you do have a question, if you could direct it at me, that would be great. I will repeat the question so the whole audience can hear. And then we will allow our panelists to provide their answers. So does anybody have a question they would like to start with, or shall I begin with the topics?
That's right.
Great.
Probably fairly concentrated toward Dr. Wise, but let's just take a general system that we want to control. And probably it has a human operator, and it used to be that the guy is holding the stick and he's controlling it. Let's just assume there's no delay. Then it started, we're remote controlling something, so there's delay there. And all these things, of course, are what at least I understand as a cyber-physical system. And how do we ensure stability and all these things on our control system? Well, we take into account maybe the transmission delay and the control has to be robust and everything is working wonderfully. And we don't have pilot-induced oscillation and all these things. That's how it's always been done. But now taking into account that things are only getting worse, we're only doing more communication and only more delay, is there a smarter way of going about designing the whole system or not? Or is it always going to be, there's a system that has to be stabilized, there will be induced communications delay, and we have to deal with it in this sort of way?
Well, you'll need to mitigate the time delay that's in the loop. So you either have to do that through autonomy or, so the human interface that then gets into the system has to enter in such a way that it can accommodate the time delay. So we have had landing systems on some small UAVs where we had about 900 milliseconds of time delay. And it required a lot of training on the pilot to land the airplane because of that much time delay. So, when the human is doing an action, right, so, the whole idea for those of you that aren't familiar with the requirements that we design in an airplane, if a pilot pulls on the stick and the airplane is slow in responding, then the pilot pulls on the stick harder, the airplane really responds, then it decides it responds too much, he's pushing on the stick the other direction, and you get into this oscillation. And if that happens on landing, very bad, right? So the Gripen, there's been lots of recent examples of those kinds of problems, and that time delay makes that problem worse. So you have to bring the airplanes in, and this is always I work in Boeing, so that's what we do with airplanes, right? So I'm sure with robotic examples in the factory is the same way. If you're trying to machine with a milling head or something like that, the time delay that's in the control loop probably plays a critical role as well. So I'm sure it's present in all robotic systems. But you have to remove the time delay, or your control system has to operate in an autonomous mode where you can mitigate that time delay. So I really don't know any other way to solve that problem. It's a key. You provide the interface as a decision-making interface versus as a feedback type interface. I don't know if that helps or not.
Is there another panelist who would like to? Okay, are there other questions from the audience?
Well, let me just comment something there. I have nothing to say about the humans. I mean, I have problems understanding bacteria, and so the humans are just beyond me. But just about the issue of delay, and there's communication networks into several different things other than delay, drops, etc. I think there's an opportunity to go. So one option is to you go and look at your network control system and you characterize what's the maximum delay, what's the distribution of delay, etc. And you try to get a system that's robust with respect to that. There's something I find more exciting is to actually sort of work together the development of controllers and the development of protocols that would sort of do something better than just creating delays. So let's say a protocol that takes into account that a particular feedback loop at this particular time instant, because it suffered a lot of noise, needs to have its message going faster. It could be just as simple as a priority, but perhaps adjusting the priorities based on knowledge of a feedback loop. So I think it's more exciting to do joint design of controllers and communication systems as opposed to just design controllers that are robust with respect to communications, regardless of what the communication system is doing. I think very exciting from a research perspective, but difficult because now you have two difficult problems that you have to combine.
Great. Yes?
This is actually for Dr. Spanian. You mentioned that you do backstepping with these stochastic hybrid systems. And so I know Donna Del Vecchio has a very simplistic, she basically designed it like an operational amplifier. It's high gain protein circuit you're doing a buffer. But it uses a really simplistic model of these proteins. Have you thought about synthetic biology applications actually using these SHSs for design?
Yes, yes.
In biological cases?
Yes, I know exactly what you're talking about because we have been thinking about stochastic versions of that. So I have a student looking at that. To be honest, whenever you have someone like an engineer, and if you look at the questions I was asking, it's always kind of in the back of your mind design, right? I mean, I'm always talking about reducing noise, and okay, I can think about devolution. Did devolution do a good job at reducing noise? But when you study problems from this perspective, it's kind of always in the back of your mind how you go about designing the systems. Right? We're probably very far from having very specific medical applications to this, at least in my work, in my specific work. But I think it's in the back of everybody's mind, doing design.
So I'll present a question now to the panel. Our sponsor from John Deere last night at the poster session explained that she had difficulty explaining to her business superiors what cyber-physical systems are. However, she said that technical employees seem to wear it as an old hat, but really couldn't explain exactly what it is. How do you explain what cyber-physicals are to your business superiors? So Professor Sanders, can we start with you on your definition of cyber-physical systems?
I don't have any business superiors.
I was going to ask, that was the most difficult.
Being a professor, I have no business superiors. You know, there's a lot of, I think I'll just answer very quickly because one of the originators of the name sitting next to me, and I have to be very careful, but I think there are some things that require precise definitions, and us as engineers want to have precise definitions, and I think there are some things that are purposefully and appropriately more nebulous. So I'm not trying to dodge the question, but I'm saying very seriously, I think the fact, although Helen said, and I was a little surprised, I guess I'm a geek, she said, you know, Congress doesn't like cyber-physical systems because it sounds too geeky. I mean, from my point of view, it is very nebulous, and it's very nebulous on purpose. But being one who believes that in a very broad view of what we mean by system, being one who has a very broad view of what kinds of properties those systems should guarantee, whether those be availability or security or performance, correctness, we can go on, safety. I like the term cyber-physical systems because it allows one to think very, very broadly. So for example, we just heard about that it was exciting to think about control and protocols together. Well, we also have to think about real-time timing in the processor that this whole thing runs on. And we have to think about the delays of the human in the loop. And we have to, there are many, many, I think as we start to think, and one thing I've done, and I came from a stochastic process background many years ago, was very happy proving theorems left and right. Now I've sort of gotten engulfed in this power grid application. This is an incredibly complex system, and it's I mean, it's hybrid in the sense we talk about hybrid systems. It has humans involved. It's hierarchical. In just so many ways, it's complex. And I think cyber physical systems, as Helen said, it's not just building another RTOS. It's about thinking very holistically about systems as a whole, systems that have cyber and physical parts. Now we're sometimes talking about cyber physical human systems, and the kind of work that I'm doing has humans as well. And really ensuring that these systems provide certain properties globally, again, where there's a very holistic view of what those properties are. So I don't think I answered it too precisely, but we'll see what the
instigator is the right way to
the
describe
instigator
it.
thinks about all this.
So actually, you did a pretty darn good job,
Oh,
Bill.
good.
I
Thank you.
think what we were up to was trying to deal with this separation that existed, and in many cases the disregard for the computational role in all of this. And so what we were trying to do was treat this as a joint problem of computing, communication, and control, and try to pull it together in a way that that achieved really a new system science that drew these together. That's what I mentioned in our in the opening statement at this meeting. But I think that's a huge challenge, and to formulate all the kinds of methods that can play in this at the outset is nearly impossible. The one thing that we did not want to have happen was for this to just become a drill in, oh, it's control, or oh, it's real-time systems, or it's, you know, that kind of tug and pull. Rather, we wanted things to start to come together, and we've seen some very nice evidence of that. I think so. Some of the work on delay in sensitive systems plays here. The observation, and so that's kind of the control response to the fact that there's latency in the system. The sort of standard statement by, and you may not know this, I don't think there are too many real-time systems people here. There's a standard little quip by real-time systems folks that real-time doesn't mean fast, necessarily. It just means when it's needed. And so there's work on describing timing of things. The work on logical execution time that Tom Hensinger did, that is actually giving, instead of just computing as fast as you can and then immediately doing whatever it is you're going to do, actuate, for example, you actually arrange it so that you actuate at a precise time, so that that time is known in terms of modeling the dynamics of the system. So what we're really up to is creating this intellectual culture that brings these questions together into the same crucible and works on them together. Now, I was really taken with what Joao was describing, because I think he's taking things from the standpoint of, you know, having this complex dynamics with a large part of the description counting on noise, and then breaking it down gradually so that you're eliminating the presumption that everything that's happening that you can't explain so far is noise, and turning it into a more precise description. I think there's a huge role for that thinking in discovery, in biological discovery, but in a lot of other areas. And this area, I think, can become a tool of science as well as of engineering. So, you know, I mean, really what we're up to is this combination of the artificial and the engineered or the natural, and coming up with ways to describe systems. And they're not easy systems. So this kind of cooperative system, coupled system description is essential to it. So if you ignore the dynamics, it's not a cyber-physical system. If it's just something easy where you're going out and doing a lot of sensing, and, you know, it's easy sensing, you're just making data streams. That's not readily accepted as a true cyber-physical system. Anybody else? You know what? Actually, it'd be great if people argued for better definition.
No, but I think purposely we don't want the definition to be too precise.
Too crisp, exactly.
You know, the way I've heard that from the my real-time friends, it's real fast is not real time, right?
Yes, exactly.
And I think
Yeah.
it's really important,
Yeah.
what you said about that.
So we have a follow-up question to that one. So many examples of cyber-physical systems have been discussed during the symposium. So can you possibly discuss a problem or a system you have encountered which you think may have been misconstrued as a cyber-physical system. And Helen, you just touched on this, but maybe...
Are you talking about all those rejected proposals?
You're not allowed to talk about that.
I can't. Let's see. So I'll answer that from the standpoint of the program. So the things that are not faring well, and for good reason, not faring well, are those that simply solve one problem and don't build towards the science. So if you bring us, a really good solution for controlling one building, and making it a smart building, that's probably not done in a way that helps us generalize much. So please, as you're bringing us proposals, do try to think about what it is that is the underpinning insight that can be turned into part of the science for this area. So that's my answer on that, I think.
Can I turn the question around? And so, I don't know whether I even need this, but in terms of modelling, so there's been, the program's been in existence for a number of years. What are the simulation tools that are available that are capturing both the physical dynamics along with representation, a consistent representation of the cyber infrastructure as well? Because I'm seeing a lot of people who are talking in the cyber infrastructure and where it's particularly stochastic, that's their modelling framework. I'm seeing people talking in hybrid systems, hybrid dynamical systems, where there's the switching and there's continuous dynamics, but that's not really representing the cyber infrastructure. But I'm not seeing too much that's bringing together that the both parts of it as from someone who actually wants to simulate systems.
So I think we're 3 years in. And the first year, almost everyone was sending us projects as opposed to science. We're making progress in terms of having, for instance, there are groups that are trying to begin formulating methods for modeling things. I don't think we will have mature tools for a while. And I'm going to digress a little bit because I think there's some barriers to having mature tools. I have to be careful how I put this, but I think the commercial tools that exist, everyone's been rather stuck with using those because you can't rebuild to start thinking about this. So everybody's pretty much in the same position with respect to the starting tools. I think there have been a lot of new ideas that have come out that are not well incorporated into that, and Kevin mentioned that they aren't really top-notch with respect to representing all the aspects of hybrid systems. But I think there are a lot of the work on efficient computation, LMI, and SOS, and so on, those things aren't as available to us as they ought to be for really doing good reasoning about these kinds of systems. So I agree with your wish for this. I think what we have to have is more help from agencies who can actually direct the research more, or we need the community to come together around a tool building activity. And we have not seen a proposal along those lines. So that's a great space. In fact, I can't talk about a solicitation that's not yet issued, but I can tell you some of the things that we are a little disappointed about. We have not seen much work on platforms, and we have seen some very nice work on ideas, modeling principles,
what do you mean by platforms?
even execution platforms, but also tool platforms. And I will say that some of the ideas, cyber-physical systems ideas, are materializing other places. I think there have been nice experiments in the DARPA Meta and IFAB and Avium area. But what I really think we need is some community-based open source and open modeling activities that would help us make the very more directed progress towards capturing the science that's beginning to emerge. So I think that is a gap. I think when you see the solicitation, you will see that, I hope you will see that what we really want is things that enable the science and engineering. And so it's, you know, please do send us those kinds of ideas. And we've been very emphatic that these need to be interdisciplinary teams, that these can't be just cyber-only imaginations of physical systems, that they have to be grounded. So that's, it's a hard balance, and everybody knows that a really jazzy project that has a really jazzy problem, target problem, is going to sell to a panel. But this time around, I think we really have to focus on bringing together the science in a better way. There's a real bootstrapping problem with programs anywhere, at NSF, at DARPA, everywhere. And so I think we've been through our bootstrapping phase, and now we're at the point where we really expect to see more convergence of ideas. And I will mention that, I mean, I think some of the things that I'd point to, and I hate to do this because if I start on one, I have to start on a whole lot of them. And I'll start by picking on a project that's not a CPS problem exactly yet. It's a career project that Cyan has that is really trying to bring together verification, hybrid systems, but considering some of the dynamics problems too. So he's doing robotics and things. But also there's a large project on using passivity. It's got networking, it's got passivity and control, and it's got a tools bit to it that is one of the projects. But I really think it's going to take mobilization by the community to get us to a place where we're collectively building something.
So maybe I can just jump in from a sort of cyber-physical system power grid point of view, and you mentioned that I think there is a lot of work going on in cyber-physical systems that may be funded by other agencies, and there's a consortium that's been formed, and I'll just mention it as an example because I'm really excited about it. There's a consortium that's been formed now with ISI, with University of Illinois, with some people at PNL, some people at SRI, to try to understand how to move the deter-type test bed into the cyber-physical world. And in fact, we have a demonstration that we're showing upstairs in a couple weeks, given it all works out, right? But that is a connection of a very fine-grained, real-time power system simulator. This is running on an RTDS. It's a very fine-grained transient power grid simulator, and a cyber infrastructure connected to that power grid simulator, executing at the protocol level on a bunch of virtual machines controlled by deter, and really understanding. I mean, you might say, oh, that's just plumbing, how you hook that. This RTDS is a rack in itself of special purpose hardware that, you know, costs $250,000 or $500,000, and it's connected to another rack that's running all these cyber simulations. But there are as you point out, Helen, it's not just plumbing. There are really fundamental questions about time and how you hook these things together that are being addressed in that consortium. And so that's very exciting to me. I think when you couple a real challenge problem, that's a problem people really need to be able to solve with people who do good theory, then that's where you really get the excitement.
And so if I could respond just quickly, I completely agree. And so I think having extremely good problems here that will push the mathematics and push the real-time systems work is extremely important. And so the things that Ian was describing about, you know, trying to balance dynamically intermittent sources and loads and make those, you know, load following sources, source following loads, what's the combination, what do we do with this? That these are problems that are really hard ones that almost demand this kind of thinking, where the computation has to be responsive, and yet it's limited. The control has to be responsive, and yet it may be limited. You may have actuation limits. You may have, you know, participation limits. So I think it's an exciting area for trying to mesh this and be able to move the constraints back and forth and end up with responsiveness in any area that you may need it.
My question is kind of related to the first question about the definition of cyber-physical system. Maybe I got it wrong, but hybrid electric vehicle that many people believe that it's a breakthrough in history. Their mass commercialization is a breakthrough in history. But since yesterday, I didn't see any presentation specifically on that subject. Could you please tell me why do you think it does not fit to this class of systems?
So the question was, why do hybrid vehicles, or why were hybrid vehicles not present in the presentations that we saw this week, and if they're not,
Or they don't fit Helen's definition, I think, more specifically.
Well, so hybrid, unfortunately, is used everywhere. But I actually don't think they don't fit, because there is, a pretty complicated control relationship, depending on how you approach it. I mean, you may just augment. But if it's full hybrid, you have this delicate dance between the electrical and the other form of propulsion. And I think leaving it the other form of propulsion is an interesting question, because I think you're taking it almost over to Ian's question, which is if you have the potential to generate electricity, and you will be consuming electricity, how will it be generated, how will it be consumed, and in this case, how will it be stored? And will you be able to take advantage of things like regenerative braking or whatever other physical phenomena are available to you for scavenging? And so, I think it's a great problem, target problem. And I think, though, the question then is, what's the orchestration that has to be done? And what's the computational role? There may be a communication latency role. And I think another interesting possibility, and I want to see Kevin's face when I say this, is that EVs and PHEVs might appear in the airspace at some point. This was a premise that was pretty much discounted about back when I was at DARPA. But I think now there's much more discussion of that, and even JPDO is talking about electric vehicles. And so I think there are tremendous
The Vulture is an electric vehicle.
Yes, okay, great. But so in the airspace where you have to have the dependability requirements too. I mean, in CONUS where
No, clearly it's a prototype. I mean,
Yeah.
it's a demonstrator. It's just we don't even have tools that in industry that support the design of those kinds of aircraft.
Yeah.
So one of DARPA's goals is to get data from the program just to validate tools that will allow contractors to build such vehicles.
Yeah.
So,
Could I add that it's not just hybrid electric vehicles, that your standard petrol-driven vehicle, the Ford Focus, one of the Ford Fusion, has 11 million lines of code that's making it
Good
work.
Yep.
And that's just a gasoline, your average. I forget how many hundreds of microprocessors there are on board, and there's this CAN bus that is communicating, and you find things like, what was the Prius under certain conditions, the the brakes didn't work, or you get these really weird types of things happening because you can't check all of the possible sets of conditions associated with vehicle conditions, vehicle running. And then you add to that the complexity associated with power sharing between electric motors and gasoline driven, and all the extra things that go into the electric vehicles, and it's pretty complex.
All I was going to say is it might even, I don't know if it's 11 million, but it might even be more. I mean, I remember being amazed when someone told me there was, I think, 4 million lines of code in a switching system 5 in probably 1980 or something. I mean, there's probably close to 11 million lines of code in a flat panel TV these days. I mean, it's just phenomenal, the amount of code you have to deal with.
And so to add to the numbers game, some of Kevin's colleagues were telling us that there's something like if you count them all, about 3,000 different design tools involved in production of their systems. And it's cacophony. And so, some of them are very specialized, and so I think we're counting things that are that are not, you know, general purpose design tools probably, but still 1,000 or so very general purpose things. And most of them probably go after a single angle as opposed to the, you know, any kind of an integrated method for doing things. They come from different sources, and there are lots of issues having to do with trust of those tools. Probably less for Boeing's because they're probably very, very careful about it, but not everybody can afford that. And I wanted to just take the opportunity to say that in this context of discussing automobiles and aviation, the U.S. Car Consortium asked us to do one of our workshops with them. And aviation folks came. They asked the FDA to come. And so that was a really terrific experience because it was kind of everybody in the same room confronting the fact that they all have about the same needs for design. The one thing that's interesting is that it's medical devices and systems where there has not been much work on what we'll call health management systems in the sense that Kevin was talking about. And so, you know, reflective, self-assessing medical devices, it's a big gap. So I think there's a lot of space for some joint work on things.
Dr. Ely?
So I want to follow on with something that Kevin alluded to a little earlier. When the conversation happens about cyber-physical systems, and we start talking about the computing and communication and control, there's a lot of talk about sort of what I would call the ones and zeros and getting ones and zeros around. And there's even talk about the actual physical systems they interact with. But part of that physical world that I don't hear talked about as much is that human aspect that you talked about with the PIO when they're coming for landing it. One of the things that I'm sort of thinking about is systems or areas that have what I would consider sort of larger societal impact. They have to be kind of couched in a framework that is relevant to a large section of society. Otherwise, you'll just have a bunch of us geeks sitting in the corner that bang out a solution, and lo and behold, the marketing folks will take all the credit for it. How do we go about and have that human on the loop, or human in the loop, however you want to talk about it, as part of the physical part, or possibly even some type of information processing part of our cyber-physical systems? Not just how do you do it in an engineering sense, but how do you make it part of the conversation that this really impacts everybody.
You want to take that one?
I'm not sure that I have the answer to that. I mean, humans are ingrained in our products, right? So we you know, the automotive industry clearly is the same there too. You know, we all have different design principles for how we interface, and you know, I'll just say the ergonomics that the auto industry is looking at is much different than what, you know, we're a safety-minded industry. We can't have accidents because it causes large loss of human life. You know, the auto industry tries to do the same thing, but they can't control the fact that we have accidents, right? So, you know, the previous comment that talked about the Prius and some of the testing, you know, I think if they tested their cars like we test commercial jets, that they would find all these problems. You know, we put aircraft, we discharge lightning on these airplanes and make sure the computers work, right? I mean, so it's how much do you spend? I mean, it's all about the safety and what do you do? And, you know, I think once you, I'm not advocating that they have to do that with cars, but I'm just saying that that's how you put these cars in electromagnetic fields that are they're gonna find things. You got CAN bus all over the place. Those are issues, you know, the EMI problems. We have them on our vehicles as well. So dealing with these problems, and then it's always when the human's involved, dealing with problems is where the cost really, you know, because with good day, it's typically affordable for us to develop things for good day scenarios. When you have a human in the loop and you're starting to address bad day scenarios, like things going wrong, that's where the shortfall usually is, and that's probably one of the most important areas, is being able to address when the things don't work right, you know. NIRA's adaptive control. You know, we're trying to use adaptive control to help mitigate all of these things in our airplanes now, and we're finding that we've actually taken it into production systems. So there's progress being made, but in terms of designing vehicles, it's still a major challenge.
How do we design it? Humans have very interesting behavior. Or, you know,
Well, we have a problem with pilots. You know, you bring in 10 pilots, and they want 10 different designs. They never agree. So the military, you know, writes these standards and tells industry, they kind of and see themselves, you know, they write these standards and say, design the airplane like this, so when he pulls on the stick, he gets this kind of response, and we'll train the pilots to do that. And if they don't like it, then they won't fly, right? Those kind of things. But the auto industry is not that way. So, not that that's the only industry. You know, this question about John Deere, you know, I saw a video recently on the internet where the wagon automatically came up next to the combine. I mean, John Deere's doing great. I missed yesterday, so I wasn't able to talk to the John Deere people. I don't know if they're still here or not, but I saw that video. Someone sent me that at work. My family comes from a farm, so you know, I watch those kind of things. I thought it was amazing, the technology that John Deere's bringing. So I'm surprised that she would make the comment that she couldn't explain to her superiors what cyber physical systems are, because tractors really are. They are that.
actually, Kevin, if you look at the all issue of the NA bridge, it's all about information and agriculture.
Oh.
How those two come together. And they talk about it both from sort of like the seed and biotech and research space all the way to machine mechanization, automation space. It's actually, there's a lot of cyber physical activity that will go on in that supply chain is the way that IBM Smart Planet people look at it.
You know, I would imagine that as our age groups, you know, my dad is 88 years old. He just retired last year. He likes to kick things. He's used to working on combines, you know, those kind of things. So, you know, my brother who's taken it over, he doesn't work on things. He'd rather hook a laptop to it and have it be diagnosed, right? And so you just look at the generations, how they're changing. I think that's really how we're all evolving, exactly right. The iPads and the iPhones and those kind of things.
You know, I think it depends on where you sit in John Deere, like any company, and I'm sure you know that. I mean, there's certain, I mean, there is a office of John Deere in town here that employs quite a few people, and there are a lot of, including people I see in the audience, who have projects in cyber physical systems, like I think you, Cyan, right? Working with John Deere on exactly these kind of problems. So some people in John Deere really understand.
Oh, sure, yeah.
Some may not.
They are actually very much interested in this problem of integrating the human in the
Yeah.
loop. The other thing which I found interesting in talking to them is they're trying to automate how agricultural fields get plowed, for example, based on GPS information. So the tractor would automatically change the depth of tilling. The other thing that I found sort of funny, and anecdotal, talking to my collaborators in John Deere, is the following. So they have the ability for the tractors to, basically they have autopilot on the tractors. So the tractors can go from point A to point B automatically. They also have the technology to make the tractors stop when they sort of come close to an obstacle or a ditch. But they don't implement that because of liability reasons. So if you try to stop and somehow fail, you can get sued. So all safety requirements are relegated to the operator. Okay. So that's potentially an area where, you know, automated software engineering or cyber physical system, for example, reliability could aid design of systems.
But to follow on, Simon, with what you're doing, and I also have a project in this area with John Deere, that there's no escape. Even the buttons, the control panel, you know, it's not a steering wheel. The touch panel that you drive a tractor with, if there are design issues and you got it wrong, and there are liability issues. So I mean, it's really exciting to me because I work in the area of trustworthy systems, and the idea of this very complicated cyber physical human system and all the trust and specifically safety issues in doing that. I mean, that's first class on their mind, and modeling all of those things in a first class way. So yeah, it's.
So I'll just say I think this has been a great discussion of this. I think the there are some places to make some inroads, and the whole problem of authority sharing in systems may be one of those places. So if we have UAVs that are autonomous, then the question is, how do you design behaviors so that you can have appropriate interventions and make sure you can make that safe transition to another form of operation, either guided by another UAV or by a human, and achieve something that is at a level of abstraction that could be understood quickly and then managed appropriately. So, you know, if you're not strong enough to steer that car to the off-ramp, you're one class of human being that doesn't have control authority in that sense. If you're not authorized to be doing something on the road, you know, in the cybersecurity sense, that's a different kind of, it's a nice pun, I think, control authority. And so I think trying to bring these issues together so that skill, you know, understanding of the system might, a really well-trained operator might be able to work in certain modes. Somebody with lesser skills still might be able to handle a system to a certain extent. I just don't think we have examined all these trade-offs and the kinds of behavioral descriptions of systems that could enable it. And you know, unfortunately, there were programs a long time ago trying to do skill ratings at NASA Langley that I think have left off. Also, condition assessment. So, you know, if Ford's going to put in your steering wheel the ability to see whether you're having a heart attack or your glucose is way off and you probably aren't in condition to be driving, then, you know, what are we going to do? I know, but it's actually a discussion that's going. It's a discussion that's going on whether this, in fact. So we've been having some meetings, and Ford is actually sending. I think there's discussion with the FDA about these things. So if you can talk to Bill Milo about these, are really, really interesting problems that they're thinking about.
I think it's a function of what the economy can. I mean,
Yeah.
there are economic aspects to it. The building automation systems are very poorly designed for both the operators and the occupants, but the economics does not support probably enough research to make it better. So that might be one reason, which might change because energy prices are becoming more expensive.
Yes.
I have a question kind of for us budding academics and industrial. So we kind of have the two different sides of cyber physical systems. We have the fundamental sciences at the bottom with the modeling and stochastic systems and hybrid systems. And then we have all the problems we saw from Xerox, Boeing. As a person up and coming, do you see it more fruitful to kind of start in the science and find the problem that the science that we were developing fits? Or do you think it's more kind of fruitful in the long run to start at the top and say, who has the answer to my problem, or how do I have a problem, how do I solve it? I'm kind of interested to hear not only from NSF's point of view, but also maybe Boeing's and also something.
I can jump in. Actually, I generally like better the approach of starting with a problem. I mean, inevitable then you'll find something that you have this hammer that you're going to use to hit on every nail. But chances that you're going to find something I think really exciting probably will come from a problem. At least that's my experience. Starting a problem. I started working on network control systems completely by accident. I was working on robotics, vision-based robotics, and I was getting all these problems. Because you have some camera off the robot, trying to control the robot, and I get these delays, crazy delays, which came out. It took me quite a while to figure out that there was packets fall, wireless link packets were dropping, and the first reaction was, this is just not very. So I mean, let's just get the stronger transmitter and not worry about it. But then as you start like looking at it, you realize, well, man, there is a research problem here, and that was actually the start of my work on network control systems. And I think it's much more likely that you'll find something exciting. That's my.
So I'll say I agree. I mean, that's what we mean when we say translational research, is we're trying to find problems that expose some need, some gap in the science, and then feed that into some aggregation of the science. And I think you don't just start and say, wonder what the science should be. I don't think you get there from here. So that's.
But sometimes the science is inspiring for solving problems that you had, that I'll just say the science had no intention of contributing to. You know, so we've been trying to think of, I like to use Chris Burns as an example. And, you know, he was doing some really great work, and which had nothing to do with flying airplanes, right? But it inspired us to think of the vision is a flight control system where you could never depart controlled flight. So it's like put yourself at the goal. This is what we typically do in industry, right? Put yourself at the goal and try to work back. How can we create such a thing, right? So, and how could you come up with a feedback strategy or a control law that would lend yourself to such a vision, right? Those kind of things. And he was doing a lot of work with periodic orbits and unstable equilibria and things. And, you know, so just talking with them, next thing you know, we write an AFOSR proposal, and, you know, we're actually creating one. It works in simulation. We're actually going to go fly it. So DARPA has agreed to fund it. It's a complete game changer. So, you know, it's ideas like this, and, you know, we would have never, you know, he was he was doing pure mathematics. I would say he had no intent of anybody using it. At least I thought from the presentation that's how it works. You know, so, but, you know, we're all in business together. You know, the business of academics and the business that's run here at the university. You know, if you look over the last 20 years, industry has really cut down considerably in the amount of basic or pure R&D that's done. You know, McDonnell Douglas Research Lab has gone away. You know, HRL has been, you know, cut up and sliced and sold off into pieces. And so the think tanks that we used to see in the old days, supporting industry where problems were solved, you know, I think those kinds, you know, like RAND and so forth, you know, those places worked with academia, and they were the liaison to industry. Now it's shifted clear to the university, you know, so now, you know, industry is looking for the schools to come up with the solutions to the problems, you know, and you have to do science too. So, you know, oh, by the way.
So maybe as well, there are several of us certified academics on the panel. I'll say I don't disagree of anything that's been said. I mean, clearly there's lots of theory you can do that will solve no problems, at least not today, and maybe in the future it will, but you don't know. You know, people always say, should you do applied research or theoretical research? Should you do, and I think it's really the wrong question. I mean, I think for me, you start with the problem, you think about solutions, then you go back and forth all the time, and then you start thinking about theory. And, you know, the good thing, one thing I do tell my PhD students is you don't have to solve a particular problem. You just have to solve some problem, and some important problem. And, you know, so you absolutely have to be motivated by real problems, I believe. You know, it's what we really try to do here at CSL. You know, good fundamental research that solves high impact problems. But there's some variability in what the problem is that ends up being solved, and hopefully that you don't just have one hammer. There's still also a lot of vulnerability in what good theory that is developed and used to solve it. So for me, it's not one direction or the other. It's really taking a broad view where you just say at the outset, it's only interesting to me, this is a requirement I make of my students, it's only interesting to me if there's really good science and there's really a high impact reason to be doing it. And then it's not one or the other anymore, and you kind of go back and forth until you hone in on, you know, on what it is you're going to do. So I don't know if that's helpful, but for me, it's not one direction or the other at all.
So I'd like to add to that question. So as a student, graduate student here at the University of Illinois who sits in CSL and works on interdisciplinary problems, would you suggest or recommend any changes to the education curriculum to allow students to become more interdisciplinary throughout their studies, rather than just being a mechanical engineer or just being an electrical engineer? I know often we get the opportunity to take classes in aerospace, EE, ME, I know that I have, but I still feel like, computer science knowledge would be very useful for me. Dr. Espana obviously has learned bio late in his career because he found an interesting application.
I'm still learning. I did
Still
sit
learning.
in several undergraduate classes.
So engineers often, we need to go back and take basic undergraduate coursework in order to transition ourselves to solve these problems that we find with the appropriate tools. Can you make recommendations or possibly comment on how to change the curriculum for engineers to provide a method for us to do this?
Can I just?
Okay,
Yeah.
good.
So like Joe, it's even after a lengthy career, one is never too old to go and sit in graduate classes and learn about new techniques that maybe you learned 30 years ago and have forgotten, or maybe they didn't exist 30 years ago. But I'm not sure. One could sort of formulate that, okay, we're a little bit fixated on a curriculum. It's a lifelong learning process about what are the tools that I need and where do I find them, and going and getting those tools at the right time. So in the Australia postgraduate studies follows the British model where there's not coursework. There's no requirement for coursework, but people go off and do the courses that are relevant for their research. They still do courses, but they're very much more focused on what tools do I need to address this particular issue. And I think that's a model for life, is when you encounter a problem that you don't know about, you pick up the book and read it, or you find some source of information where you can find that.
Yeah, I agree. And I think there is room for some adjustment in curriculum. I think it's going to be a community process that makes that happen. I don't think just having, suddenly deciding that we're going to have a course or a department on CPS is the right way to go. I think the right thing to do probably is to pay attention to the things that are fundamental for this area and make sure that they're covered somehow in the curriculum. I think there's some new books out. There's a book that Edward Lee wrote on cyber-physical systems, on basically some underpinning mathematics for it. It's not sufficient in its own right, but I think there are steps in the direction of making some content accessible. And so I had mentioned before, and I really would like to emphasize the importance of mechanisms such as the Georgia Tech Summer School, which maybe needs to be ramped up and moved around, and I don't know what is the best mechanism, where people actively come together so they can teach to and be taught to. So it's a version of what Ian's describing, only it's a little more aggressively organized, and having graduate students involved in that is really important. So I'll just say that a life-changing event for me was going to the summer school, the NATO-sponsored international summer school on control flow and data flow, which they were held every year. I don't know if they still are, at Mark Toberdorf. And TU Munich was organizing them, and U.S. students were invited, and it was really quite a wonderful experience because you heard people talking about different kinds of things, but all with kind of a consolidated theme, so that you could think about concurrency and you could think about models of computation such as data flow that were at the time not terribly well accepted or integrated. So that kind of thing, I think, is really useful.
So I'll just make 3 quick comments to follow on. First one is I really agree that these summer school kind of experiences are valuable, and I've been at them and taught at them in Europe, and so twice now, and there'll be another. We've taught intense summer schools on, if you will, the cyber-physical aspects of power systems. The last one was June of this year. We had, 130 or so people at it. There were 40 or so full-ride academic scholarships that came from DOE and DHS. And it was, 35 or 40 hours of lecture in 1 week and discussion and hands-on stuff. And it was just magical. I enjoyed sitting in. I lectured, but I also sat in all the lectures. So that's one point. Second point I wanted to make, if you say about curriculum, I really agree with what Ian said, that it's about lifelong learning, and it's about, I mean, you know, I have a computer networking book upstairs in my office that was written before, by Tannenbaum, that was written before TCP/IP was invented. You know, so in some sense that book's terribly out of date. So I'm not complaining about Tannenbaum. He has a great books on computer networking. But there's some things you can learn yourself, and there's some things that might be hard to learn. And at least for me, I always chose to take the courses that were mathematically based and fundamental, because I found those are the ones where it's really learned by doing, except instead of learned by hearing descriptions. And there's lots of things that have changed. All the different application areas I've tried to work in, you know, I can pick up a book and learn that. Now I think, you know, so I don't know, that's a way to choose. And then the third thing I just wanted to say is that, you know, most of our graduate curriculums really are pretty open. I mean, I can't remember, and I'll get it wrong and someone will tell me, but, you know, in the ECE department here, for example, I think more or less you can take any courses. You have to take courses. It's not like the British system, but you can take any courses from any department, except that 3 of them have to be ECE 500 level courses or above. And then, oh, by the way, there's a whole list of other courses that aren't really ECE courses, but maybe they're CS courses or some other kind of courses that really count as ECE courses. So it's really not very restrictive today. I mean, it's at least in many, it's very open, and you can pick what makes sense. So it really makes sense as a student to think carefully about, because you're never going to be able to take courses in everything, what will help you the most in learning how to learn, right? I mean, that's the kind of courses you should take. So,
So I agree with that. The lifelong learning is a motto that they have at the Boeing Company, and Phil Condit used to talk about that all the time. And if you look at how technology has changed, you know, and it's changing even more rapidly. You know, how do you prepare yourself as a student? What classes do you think you need to take, right? So to me, it's fundamentals. You know, it's mathematics, it's the physics, it's the sciences, it's the fundamentals. You know, I took some classes. I tried to take. I took a lot of them EE when I was here, specializing in controls, and you know, I think I've learned 10 times as much since I left school that I did when I was here at school. So things just change, and you have to prepare yourself for that change. And that's really the key, is to have that open mind and to make sure that you embrace that lifelong learning. Keep yourself attached somehow to programs where you can learn. And that'll serve you best, I think that would be my recommendation.
I'll just add that I think we do have a little bit of a gap, and that is that we have, I'll say it this way. There's the seamy side of CPS, which is the seams, and we have not, which is not yet resolved. And I think if we had some educational materials that kind of that address those linkages, and I know that for one, Joao has done some tremendous educational tutorials and educational modules, and there are others out there that would be useful, if only to promote the discussion and to start moving us towards more resources. Okay.
I'll take this opportunity to thank the panelists and also to thank all the students who traveled to the University of Illinois to attend our symposium, but it's time for us to wrap things up. I hope that you have safe travels home, and let's give our panelists a round of applause.